So today we're going to be looking further into the Poisson distribution, and we're going to be looking at the properties of a Poisson distribution. I'm going to start by referring to the binomial distribution. When we first started working with the binomial, we learned how to process the calculations, we learned how to use the function on our calculator, and then we made sure we had a good understanding of when we could model with the binomial distribution appropriately. The criteria, the conditions, the assumptions that we would need to make for the binomial to be the appropriate modeling decision. Well, the Poisson distribution has its own criteria, conditions, assumptions that you would need to know to make sure you're choosing the Poisson distribution correctly. Those criteria are that the events we're considering must occur singly in time. That means one at a time. It's impossible to have two of these events happen at once. If we're talking about people walking into a room, we'll assume that they walked in one at a time, not that two people walked in at the same time, hand in hand. This, I hope you can recall in the last video, is similar to when we said a 6-minute interval. The issue there is that we could have had 10 cars turn up. We could have had 2 cars turn up in the interval. So we needed the interval to be infinitely small, so it was only possible for one occurrence of that event at a time. Secondly, they need to be independent from each other. One of those events occurring doesn't impact whether or not the next event will happen. And these events are happening at a constant rate. So there's a certain average number of occurrences within an interval that's been specified. And that average is scalable proportionally with the time interval. As long as we can reasonably assume these 3 things, or we've been told these 3 things, then we're fine to work with a Poisson distribution. So let's see if any of these come into action in this example. So here we're told that a shop sells radios at a rate of 2.5 radios per week. So I want to start with actually getting down that distribution. So X, the number of radios that are sold, follows a Poisson distribution of 2.5, and that is per week. In part A of the question, we're asked to find the probability that in a 2-week period, the shop sells at least 7 radios. Firstly, the time interval has changed. We had the parameter, we had the average rate for 1 week. Well, now we're talking about 2 weeks. So I'm going to rewrite this distribution, and I'm going to call this X1. Well, that follows a Poisson distribution for 2 weeks. So it's going to be 2 times the 2.5. So X1 follows a Poisson distribution of 5 radios sold per 2-week interval, per fortnight. This is the parameter I should use for the rest of the question. We've then been asked to find the probability they sell at least 7 radios. So we're going to find the probability that X1 is greater than or equal to 7. We know that we need to turn this into a 1 minus. So 1 minus the probability X1 is less than or equal to 6. And on your calculator, it's PCD for the minimum, 6 for the maximum, and 5 for the average. Your lambda value, your parameter, is 5. All of this into your calculator and you get 0.2378. So there's a 24% chance that they sell at least 7 radios. In part B of the question, we're told that deliveries of these radios come every 4 weeks, and we're asked to find the probability of selling fewer than 12 radios in a 4-week period. Once again, the time interval has changed, so we want to scale our parameter to match. I had X as the original distribution, X1 as the first modification, X2 is going to be my new modification. It's going to be 2.5 multiplied by 4 to represent the 4 weeks. So X2 follows a Poisson of 10 per 4-week period. We're finding the probability of selling fewer than 12. So the probability x2 is less than 12. Straight away, I'm going to rewrite that. Probability x2 is less than or equal to 11. I'm sure you know what goes in your calculator. PCD, 0 for your minimum, 11 for your maximum, and 10 for your parameter. 10 for lambda. We get 0.06968. On to part C. The manager wishes to make sure that the probability of the shop running out of radios during a 4-week period is less than 1%. We've been asked to find the smallest number of radios the manager should have in stock immediately after the delivery. If they run out of radios, that means the number of radios that a customer has come in to buy is greater than the number of radios they have. It's going to be larger than the number of radios that they have. So if they have 10 radios, 11 customers have come in, and that 11th customer, we had to say to them, we have no more radios. So the number of customers wanting to buy a radio is greater than the number of radios in stock. And we want that to be less than 1%. We can be a bit more formal with the maths here. We can say the probability that x2 is greater than s should be less than 0.01. We know that we want the probabilities to be less than or equal to for the benefit of our calculator and the tables, so we can rewrite this left-hand side. We know greater than s is equivalent to 1 minus less than or equal to s. And from here, we're going to want to do some rearranging to make the probability statement the subject. So the probability that x2 is less than or equal to s is going to be greater than 0.99. Really, from here, we should just be able to use the tables, and we're going to go to the column where lambda equals 10. We're going to go down until we see the probability go above 0.99, and we'll track across to see what value matches. So in that case, s is going to equal 18. You could do trial and improvement on your calculator, but the tables are so much more efficient for a question like this. Okay, and then just one more example that I want to go through with you. Just paying careful attention to which distribution we need to be using and when. We know the criteria, we know the conditions for a Poisson distribution. We also know the criteria and the conditions for a binomial distribution. So here we're told that defects occur at random in planks of wood with a constant rate of 0.5 per 10 centimeters of length. So we're going to get down that initial distribution. So x follows a Poisson of 0.5 per 10 centimeters. We're then told that Jim buys a plank of length 100 centimeters. And part A wants us to find the probability that Jim's plank contains at most 3 defects. Okay, we already know the plank is longer than 10 centimeters. It's 10 times the size. So we're going to scale up our parameter. x1 follows a Poisson of 5 defects per 100 centimeters of plank. We're trying to find the probability of at most 3 defects. So that's the probability that x1 is less than or equal to 3. 3 is the most that should happen. 3 is the maximum value that should be involved. Over to our calculators. That's going to be a PCD, minimum of 0, maximum of 3, and the parameter is 5. Type that into your calculator, 0.2650. So that's the probability of at most 3 defects. Moving on to part B. We're told Shivani buys 6 planks, each of length 100 centimeters. So the 6 here is significant. That's something that should make us start thinking about which distribution to use. The question asks us to find the probability that fewer than 2 of Shivani's planks contain at most 3 defects. There it is. We should be able to put this together now. This question is actually a binomial distribution question. The 6 were the number of trials. The probability of success in this case is the answer to part A, because success is going to be having at most 3 defects. So the probability is there, and it's a constant probability. So fixed number of trials, constant probability. There's only 2 possible outcomes. Either it does have at most 3 defects, or it doesn't. This is a binomial question. There is a nested Poisson probability because the first part of the question, we use the Poisson distribution to get a probability, which then is the parameter that we use inside the binomial. So here's the distribution. Y follows a binomial where n is 6 and p is 0.2650. From here, we want to know the probability that there's fewer than 2 successes. Straight away, rewrite this to be less than or equal to 1. BCD, the minimum we're interested in is 0. The maximum we're interested in is 1. 6 is our n value, and p is 0.2650. Over to the calculator, and we get 0.4987, 49.9%. So, just be careful in this instance. Just because the question starts off as a Poisson doesn't mean it's Poisson all the way through. I would recommend you're vigilant all the way through the question. A question that starts with a Poisson can pull in the binomial distribution. A question that starts with a binomial can pull in the Poisson. At this stage of your further maths course, you are expected to be an expert in all the previous content, so it can appear anywhere from now on. So, knowing the criteria, the conditions, the assumptions for both the Poisson and the binomial is vitally important moving forward.